Hey guys, and welcome back to the Weekly G. Of course, over the last 2 weeks, I guess it hasn't been so weekly, and that's because I was traveling and then I was sick, and I tried to come up with a bunch of topics that I wanted to talk about, and all of them were kind of too hard to talk about. Yeah, and that actually includes what I wanted to talk about today in particular. But after, I originally wanted to talk about the difference between the Schrödinger picture and the Heisenberg picture of quantum mechanics. But I realized that, unless I kind of talk about the basics of quantum mechanics at all, 95% of the people who will see this probably just won't understand, what the heck I'm talking about. So I decided I should just go back and talk a little bit about, kind of what quantum mechanics is. So that's what I'm going to do today. And the way we're going to go about this is we're going to kind of try and compare classical mechanics to quantum mechanics. So let me give you the picture of what we're trying to do in classical mechanics. So all right. Okay, so in classical mechanics, usually what we do is we say, let's start with some coordinates that we're interested in. For example, if we have a particle in like one dimension, let's say that we care about its position and we care about its momentum. And then what we have is given these coordinates, we say that the laws of classical mechanics are also the equations of motion. So for instance, Newton's laws, for F equals ma, but I'm going to write those in terms of my coordinates. So dp dt is equal to m d squared x by dt squared. And you can also have like other equations of motion. So for instance, in Lagrangian mechanics, you have, the derivative of your Lagrangian with respect to x is equal to the time derivative of your Lagrangian with respect to x dot. In Hamiltonian mechanics, you have these coupled differential equations where you say p dot is equal to that, q dot is equal to that. And the reasons for these equations of motion are very theoretical. Well, Newton's laws over here were actually, I think, kind of experimentally derived, but the other ones have some actual theoretical reasoning that we think that they should be true. And they all kind of reduce equivalently to each other. But the point is that there's some equations of motion, and it's a differential equation that describes how your coordinates will change with time. I guess I should also say that you also have some initial conditions. So this is like, the value of your position at t equals 0 and the value of your momentum at t equals 0. It doesn't have to be t equals 0, but it's just some time, right? And if you combine these three things together, right, we have our coordinates, initial conditions, and equations of motion. These three, if you can solve this equation, which very often you can't, very often you can, and if you solve these, you end up getting, your position as a function of time, and your momentum or velocity as a function of time. And the basic idea is, that's kind of the problem you're trying to solve in classical mechanics, is describe your coordinates over all times. Okay, so now I'm going to talk about quantum mechanics. And in quantum mechanics, your goal is pretty much the same thing, which is you kind of want to know, where your particle is and how fast it's going at all points in time. But we're going to go about it in kind of a fundamentally different way. And so what we're kind of abstract away from these coordinates over here. And so what we're going to do is first we're going to say, instead of coordinates, we're going to have something that we're going to call a state. And I'll write it with this funny notation. This is we call these kets. And that refers to like the line and the bracket over here. And alpha is like a label for your state. It's just like the name of your state. So we have these states, and they can depend on time. So I'm going to say alpha of t, which is kind of the same thing as alpha of t, which is basically I have some state and it's going to change over time in some way. Once I have this state, the question is, how do I get back the things that I'm interested in, like the x and the p? And we say that we take operators, which is like a mathematical term. If you have operators applied to states, and you apply them to states, give measurable values. So kind of, for example, this is kind of a silly example, but so say I have my state alpha over here, and I want to get the x position. The basic idea is I have some operator x hat, and when I apply this to this, somehow this gives me x, like the x coordinate of state alpha. Yeah, and so the basic idea is, we have these states, and we can get, and given a state, we're able to use these operators to somehow get back the values that, we're actually interested in, like the position or the momentum or the energy or something like that. Let's see. And so we also need some initial conditions, which is basically what your state is at time 0. And then now, of course, you need your equations of motion, right? So equation of motion. And the idea is that instead of saying how x and p are going to change with time, instead we're going to say how this state is going to change with time, right? And that's kind of a different thing because, or like effectively this should give you the same thing, right? Because if I know how my state changes in time, and it's possible for me to get the relevant coordinates by operating on this state, then I kind of have like the equivalent thing, right? So the equation of motion that I have is the Schrödinger equation, which I'm going to write like this: I bar dt. So that's the partial derivative with respect to t of my state is equal to some operator times my state. And so this is what we call the equation of motion for states. So this is just the partial derivative with respect to t. And h hat is an operator called the Hamiltonian. And what this is an operator whose associated observable is the energy of the state. So like, up here I wrote x hat operating on alpha. Similarly, down here, I could do, if I did h hat operating on alpha, this tells me something about the energy of state alpha. Okay, so basically, I guess the idea is that quantum mechanics and classical mechanics essentially have the same goal, which is you want to figure out this x and p as a function of time. And so in classical mechanics, you kind of do that directly. In quantum mechanics, essentially what you end up getting is, this equation of motion tells you alpha of t, so which is the state as a function of time. And then if you apply, x hat to your alpha of t, or p hat to your alpha of t, this kind of gives you x of t and p of t. And I'm going to put these in quotes because they're not exactly. Okay, but this is the basic idea, which is that in quantum mechanics, quantum mechanics and classical mechanics are trying to do essentially the same things. Great. Okay, so you might be wondering, like, this seems like nothing is really going to be different, right? Classical mechanics gives you x of t, p of t. Quantum mechanics gives you x of t, p of t. And that in some ways that's kind of true, but in other, but we have to be very careful because I kind of glossed over exactly how, when you apply operators to states, you get exactly how you get these measurable values. In classical mechanics, it's incredibly obvious because the things you solve for are directly the things you care about. In quantum mechanics, the things you solve for are these states, and you have to do something to those states to get the measurable values that you're interested in. But I haven't actually told you what that thing that you have to do is, right? I've just told you there exist these things called operators. So I'm going to erase these things over here. So I can have some space to tell you about. Here, actually, let me just even clear the whole thing. Okay, so now what I'm going to do is I'm going to tell you basically like how we get these measurable values out of a quantum state. So, and this is where it gets very dicey and where things get so difficult in quantum mechanics. So the first thing I have to do is come up with like a specific mathematical way that we can talk about these things. So I'm going to say, let my states alpha be in a vector space. And this is a vector space in linear algebra. I'm not going to tell you the properties. You can look that up on Wikipedia. But basically, all of these, maybe if you took linear algebra, you said, I have some vector v, and that can be in some vector space. And, you can do things like add vectors, multiply vectors by constants, and there's a bunch of properties. There's also dot products between vectors, and things like that. So I'm just going to assume you kind of know what those are. And so we have these states are vectors in a vector space, and my operators, I'm going to use a hat as my operator. This is a mapping from theta v, and so it's a linear operator in a vector space. But basically, the idea is that if I have some random vector in my vector space, if I apply a to v, this will give me some other vector in my vector space. So that's what an operator is. And so if you take in linear algebra, you know that these operators kind of correspond with matrices. And some important things you probably did when you were studying matrices and stuff like that is you learned about the fact that these matrices have eigenvalues and eigenvectors. So I'm going to call this block 1. So block 2 is operators have eigenvalues and eigenvectors, but I'm going to call them eigenkets because I'm going to use the word ket and vector interchangeably. They just kind of mean the same thing. And so in quantum mechanics, we assume that all of our observable operators have eigenbases. And this is because, so kind of a technical digression, this is because a hat dagger equals a hat, i.e. the operator is Hermitian, and if your operator is Hermitian, then you're going to, the spectral theorem is going to apply in a complex vector space, and so you're going to get an eigenbasis that's complete. And you're also going to have, and the reason things have to be Hermitian is because because the eigenvalues of a Hermitian operator are real. So if you got that, then great. If not, you can ignore that. Just assume that things go as you expect. And so basically the important thing is that these operators have an eigenbasis associated with them. And what I mean by that is it's possible to write any other vector as a linear combination of these vectors. So say I have some vector alpha. This can be written as a sum of the ci ai's. And this is the sum over all I. And so you guys, if you're working with matrices, you are working with finite vector spaces, in which case this like 100% holds. We kind of assume it holds in all of quantum mechanics. Okay. And these things are called it's an eigenbasis specifically because if you take an operator and apply it to an vector, then the thing that you're going to get back is actually just a scaling of your original eigenvector. AI. Or I guess maybe I'll write lambda here. So. Right. And so if you remember your linear algebra, this is something you had to spend a lot of time calculating the eigenvectors and the eigenvalues of, different matrices. Yeah. And so the claim in quantum mechanics is, if, for instance, I was interested in X, I could take one of, and I had a state, alpha, that was an eigenvector of this operator X, then it's going to give me some lambda I times my original vector, and this lambda I over here is the thing that you would measure. So let me say that again. If I have a state alpha that is an eigenvector of an operator, in this case x hat, then applying that operator to that state will give me an eigenvalue, and that eigenvalue is kind of the corresponding observable with that state. So for instance, here's my state alpha. I want to know what x is, so I apply x to it. If it was to be an eigenvector, then the eigenvalue that I get back is the position that corresponds with my state alpha. And so that's kind of a convoluted thing, but if you think about it for a little bit, there's not really any other reasonable way that you could say I get exactly one number out of exactly one vector, right? And as a matter of fact, you might be saying, well, like how does that work? Because I do know that there are vectors which are not eigenvectors, right? So like if I have some vector v, well, and I can't just like only get one number out of it in general. That's a very special property of eigenvectors, right? So you can kind of get around this by saying, well, if I have some vector v, and I wrote it, actually I'm going to call it alpha. If I have a vector alpha, because my AI's over here were a basis, that means I can write my vector alpha as a sum of a bunch of coefficients, ci, times the basis vectors, right? And now, if I apply a to alpha, I'm going to get another vector, but it's going to be, because of linearity, this would be an I. Because of linearity, I'm going to end up getting a, so these are half, a times ai, and if you just apply this rule over here, I'm going to get ci lambda I ai. And what we say, so these lambda i's over here are what, or it's possible. These lambda i's are what you can observe, and what we say is that the probability of observing this lambda I is equal to the coefficient squared. Okay, and that's actually kind of just a postulate. And so this is where like the randomness in quantum mechanics comes in, because if you have a state that's not an eigen state of the operator you're interested in, then suddenly you have all of these probabilities, right? And this is actually just a straight up postulate that of quantum mechanics, the fact that you get these probabilities. It ends up being correct, essentially, because if you go through and do a lot of more math, it ends up doing everything that you expect it to, other than the fact that it's all probability-wise. But And so like the key reason that quantum mechanics kind of gets really messy here is that different operators don't have the same eigenvectors. I'm going to underline the do not. And so what that means is, essentially, if you could have a state where that is an eigenvector of one operator, but is not an eigenvector of another operator, which means you can't measure both of those two things at the same time. And so that if you understood that, then that's great. But maybe I'll try. Let me try doing this over here. So I'm going to try giving you an example just kind of in a simple vector space that you might be able to understand. So say we're in a 2D plane here, right? And let's say that we have an operator A and an operator B. And the idea is that, let's say that, you go through and you say, let's call this X and Y. And so let's assume that the eigenvectors for A are as follows, which is basically if I have A on my vector 1, 0, this is equal to lambda 1 times 1, 0. And if I had A on 0, 1, this would be equal to lambda 2 times 0, 1. And now let's do the same thing with B, but let's give it, let's give it some different eigenvector. So let's say B times 1 minus 1 is equal to lambda 3 times 1 minus 1, and B times 1, 1 is equal to lambda 4 times 1, 1. Okay, so I'm going to draw these vectors. So here's 1, 1. Here is 1 minus 1. Here is 1, 0, or 0, 1, and here is 0 minus 1. And so let's pick a specific one of these states, okay? So let's say I pick this guy over here. Then if I apply, and I'll call this my state alpha. Then if I apply a hat on alpha, I'm going to get lambda 1 times alpha, right? And that's just because I used this rule over here. But if I were to apply b hat on alpha, this is equal to b hat times 1 minus 1 plus 1, 1, all of that divided by 2, right? Just because that's equal to 1, 0. And then what ends up happening is I get lambda 3 times 1 minus 1 over 2 plus lambda 4 over 2 times 1, 1. And so the question is so when I operated A on alpha over here, I definitely get back the value lambda 1. But when I operate B on the same thing, then I'm either going to get lambda 3 or lambda 4. I'm not going to get both, but I'm only going to get one of these two numbers. But what ends up happening is and then the problem is that you have different probabilities of getting lambda 3 and lambda 4. In this case, the way I've set it up, you get equal probabilities. But so the upshot of this is a hat. If you were to measure a with this, that would be, so, okay, here, let me come up with an example. So let's say this was x hat and this was p hat, right? This is actually not true, but let's assume that that was true for a second. Then if I took my state alpha over here and I tried to get the position of it, then I would get something like, 10 meters away from my 0 point. But if I took my p hat and operated on my alpha, and let's say, I would get either, like 5 kilogram meters per second, or 2 kilogram meters per second, or something terrible like that, right? It's like, which one of these do we take, right? And so quantum mechanics says, well, take with probability, 1/2, take 5 kilogram meters per second, or with probability 1/2, take 2 kilogram meters per second. But we don't say which one it is. But you realize that we can't force ourselves to say one of them from the mathematical framework we set up, because the only things we're allowed to measure, the only numbers we're allowed to get out of this measurement are these lambda 3 or lambda 4, and we can't get any individual one of them because, because you had to pick, because the state that you were in was not either 1 minus 1 or 1, 1. It was a combination of these two states. And therefore, it is non-deterministic which one of those things you're going to get. Okay, so that was my attempt at explaining quantum mechanics, or the goals of quantum mechanics, and a first look at why it might get weirder than you would expect from the first goals. And tomorrow, because I missed one, so I'm going to try and get another one in. Tomorrow, I think I'm going to talk about dark matter simulation, because that's what interests me the most right now. So, yeah. So thanks a lot.